In section 3.2, we are going to look at the mean value theorem. The mean value theorem talks about the average value over a specific period of time. This is a concept that is going to connect the instantaneous rate of change to the average rate of change. Let's look at an idea. Suppose a runner runs a 200-meter race in 25 seconds. Now, 200 meters over 25 seconds is an average speed of 8 meters per second. So the runner, we know, has an average speed of 8 meters per second. The question is the runner's speed ever exactly 8 meters per second? We know that when you run a race, you can run certain parts faster than the other. So is this runner's speed ever guaranteed at a single instantaneous time to be 8 meters per second? Well, that's the concept of the mean value theorem. Is the average speed ever guaranteed to be an instantaneous speed? Or is there ever a point in time where the instantaneous rate of change is equal to the average rate of change? Let's take a look at this on example 1. Let f of x be x squared plus 2x on the closed interval from 0 to 3. Let's find the average rate of change on the interval. Is there a point which has that average rate of change as the instantaneous rate of change? Let's begin by finding the average rate of change. That's going to require me to plug in an f of 3 minus f of 0 divided by 3 minus 0. So average rate of change is the change in y values divided by the change in x values. So if our x values go from 0 to 3, then the average rate of change is this slope here, f of 3 minus f of 0 divided by 3 minus 0. When you plug in 3 into the function, you end up getting a 15. When you plug in 0 into the function, you get a 0. That leads to an average rate of change, which is 15 divided by 3. So the average rate of change is 5. Now, is there a point in this interval, or is there an x value in this interval that we can find such that has the instantaneous rate of change is 5 at that x value? We know the instantaneous rate of change is the derivative. So is there a point where the derivative of x is 5 in the interval from 0 to 3? We can do this algebraically by taking the derivative is 2x plus 2. If we set that equal to 5, we can solve, and we can see that 5 minus 2 is 3. Divide by 2 becomes 1.5. What's this mean? This means that the instantaneous rate of change when x is 1.5 is 5. So there is an x value whose instantaneous rate of change is the same as the average rate of change over that interval. Notice that the x value is in the interval. Let's take a look at this graphically. I've went ahead and graphed the function. The function's graph is a parabola. What I've done is I've taken this blue line segment, and this blue line segment is the line segment from 0, 0 to 315. So it is telling me the slope of the average rate of change from x equals 0 to x equals 3. The other thing I've graphed is this tangent line. I can grab the point and move it along this curve, and you can see how the tangent line changes. One way to think about the mean value theorem is to think of it graphically like this. As I grab this point, is there ever a time as I move along this curve that the slope of this tangent line is the same as the slope of the blue line segment? And it turns out, obviously, there is. We know that when you zoom in and you get to 1.5, you should end up with 2 lines that are parallel. And if you think about it, obviously, if you think about in terms of running a race, this person is starting out at 0 a little bit slower than the average. But as you go, the instantaneous rate of change gets steeper and steeper. And at some point on this function, the instantaneous rate of change matches up with the average rate of change. We did example 1, both algebraically and graphically. Sometimes you'll want to just focus on the algebra, and sometimes you'll want to just focus on the graph. I want you to think through this example 2. Let's do this together. We let g of x equals 2 divided by x on the closed interval from -2 to +2. We want to find the average rate of change on the interval, and then we are going to ask, is there a point which has that average rate of change as the instantaneous rate of change? Let's take a look. We begin by trying to find the average rate of change. The average rate of change is the change in y divided by the change in x. So I plug in 2 into the function g, and then I subtract what I get when I plug in -2 into the function g. Then we divide by the x values, 2 minus -2. So when you plug in +2, you get out a 1. When you plug in a -2, you get out a -1. Then the denominator is a 4. So we get 2/4 or 0.5. Can we find something with an instantaneous rate of change of 0.5 on this interval here? We can think through this graphically, but since we know how to take a derivative of 2/x, I'm going to do this algebraically. So g of x as a rewrite is 2 times x to the -1 power. That means the derivative of g is -1 times 2, which becomes -2, x to the -2 power. And we're asking, is that ever equal to a positive 0.5? Well, we can divide both sides by -2. If I divide 0.5 by -2, I end up with -0.25 equals x to the -2 power. If I solve this, there's a number of ways I can do it. I am going to think of x to the -2 power as 1 over x squared. Notice what's going to happen here. If I multiply x squared on both sides, I end up with -0.25 x squared equals 1. I then could divide both sides by a -0.25, and I would get x squared equals -4. Another way to see that is 0.25 is simply 1/4. So we're saying, can -1/4 ever be equal to a positive 1 over x squared? And the answer is no, if we're using real numbers. If we're using real numbers, we can't square something and get a negative. So algebraically, there is no x value that works here. Let's think about why that is graphically. I have set this up already. You can see the graph of g of x equals 2 over x is this purple function. This purple function has a discontinuity when x is 0. The limit as x goes to 0 from the left is negative infinity, and the limit as x goes to 0 from the right is positive infinity. Notice that my interval from -2 to +2 contained that discontinuity. Now, the average rate of change from -2 to +2 is graphically demonstrated by this blue line segment. You can ask, if I take a point on my graph and I start moving it, will I ever end up getting a tangent line which is parallel to that blue line segment? And you can see that it's not happening. You can see that anytime we are from -2 all the way to +2, the function is always decreasing, except like at this discontinuity, the function doesn't exist, but the function is decreasing, it's going down. And this line segment is increasing. So this line segment has positive slope, but every tangent line is going to have negative slope. And so that's how we can see graphically that the average rate of change on this example will never be equal to the instantaneous rate of change, because we have this discontinuity throwing things off. So in example 1, we did come up with a point where the average rate of change was equal to an instantaneous rate of change. In example 2, there was no point on our interval where the instantaneous rate of change was equal to the average rate of change over the interval. I would like you to attempt this problem. Take the absolute value of x on -1 to 4, find the average rate of change, and then ask, is there a point which has that average rate of change as its instantaneous rate of change? This one will probably be best done if you graph it, but you can also do derivatives if you're willing to utilize the absolute value as a piecewise function, the portion below 0 and the portion above 0. Go ahead and push pause and do this problem.